Hello everyone, today in this video we'll be discussing the second module of DSA, which is related to queues and linked list. Okay, so this has some topics, and these are some topics. There are different types of queues and linked list we'll be discussing. If you watch this video till the end, easily you can score more than 80% marks in the exam. Make sure hit the like button, subscribe to the channel for more videos like this. Without wasting any more time, let's get started. So the first topic is the queues. Okay, so what is a queue? A queue is an ordered list in which the insertions and deletions take place at different ends. Okay, so this is a queue. Okay, and we'll be inserting and we'll be deleting from one end. Okay, so that is a queue, and queue is also known as first in first out, FIFO. Okay, so let's have a look at how the queue is. So queue will have the first in first out. Okay, but before that there will be two pointers. Okay, one will be at the front and one will be at the rear. Okay, whenever we want to add an element, we'll add from this side. Wherever the rear is present, we'll be adding an element. Okay, we'll be adding the elements, and we'll be deleting the elements from here. Okay, we'll be subtracting or deleting the elements from where the front is pointing. Okay, so this is the functionality of it, and this is first in first out. That means the element which is the first inserted, that is the one which will be first deleted. Okay, for example, when I insert one number here, let's have a look at the following example. Okay, insertion of elements in the queue. So the question is, insert 2, 7, 4, 11, 1, 39, 21 into the queue. Okay, so front and rear pointer will be initially at the -1 position. Okay, f is equal to -1 and r is equal to -1, which denotes it is an empty queue. Okay, then we want to insert an element here. Okay, we'll be inserting from here wherever the rear is pointing. Rear will be incremented, and here rear will be pointing, and we'll be putting the element here. And if you want to insert the next element, which is 7, we will be incrementing the rear to this point, inserting this element. The next element is the 4, we will be incrementing r, and we'll be putting the 4 here. Okay, so this is how we will be inserting. Remember that first 2 got inserted, then 7, then 4. 2, 7, 4 is the order, and deletion will also be happening in the same order, 2, 7 and 4. Okay, now after inserting all the elements, we'll be having a queue like this: 2, 7, 4, 11, 1, 13 and 21. Okay, and to delete the elements, we'll be using the f pointer. F will be incremented, and wherever f is pointing, that will be deleted. Okay, first f will be pointed here, and this will be deleted. See, first 2 got deleted, then f will be incremented here, and 7 will be deleted, then f will be incremented, and 4 will be deleted, and so on. So it will be deleted till this point. We had the question to delete it till 11 only, right? So this is the one final position here. So this is how the first in first out happens, and this is how queue works with front and rear pointer. Okay, next, C implementation of queues using integer array. Okay, so if you want to implement it using an array, we'll be creating an array of some size here, and we'll be having two pointers f and r, which will be initially pointing to -1. So when the queue is empty, the queue is empty means there is no element in the queue. It is called as queue underflow. And when the queue is full, when the queue has all the elements filled in it, that is called as queue overflow. Okay, now let's have a look what is the coding perspective. For the insert operation, how will be the code? We'll start from here. Void insert, this is the function name, and we are not returning anything, so it will be always void only. And int item. Okay, so this is the item we want to insert. So item is a variable which has some value, like for example, item has a value 6. Okay, so 6 needs to be inserted. Now the first check what we need to do is if rear is equal to size -1. Size -1 means the last position. Okay, if rear is present here, that means we cannot add any more element. There is no space present here. That is the thing which we are checking. If this is true, means the queue is full and it will print queue overflow. Else what will happen? Rear plus plus will happen. Rear is present here, rear plus plus will happen, and at this position the element will get inserted. Okay, queue of rear is equal to item. Whichever item we passed here, that will be taken here and put inside queue of rear. Okay, to delete, what we will do, void del, and int item delete, we will be storing the item which is getting deleted in the item delete. If front is equal to rear, when will be front equal to rear? Front will be equal to rear at the starting position. When there are queue is empty, at that time front and rear will be at the same position, right? So that is what front is equal to rear. If that's the case, queue underflow will be printed because there is nothing to delete, right? And we'll be returning 0. Else what we will do, we'll do front plus plus, wherever we are front is present, we'll do front plus plus here, and that element will be deleted. Okay, item del is equal to queue of front. Queue of front will return 2, and 2 means that item is getting deleted. Will be returning to the user that 2 is getting deleted. Okay, for the display operation, what we need to do for the display, first we'll be checking if the queue is empty. Queue front is equal to rear, that means the queue is underflow and it will not print anything because there is no element to print. Else what we will do is start a for loop. The for loop will go from front plus 1. Front plus 1 means if front is present here, front plus 1 is the first element. This is the first element which is presented, front plus 1. We'll start from there. We'll check if it is equal to or less than rear. We have traversal here, and we'll be each time printing this one by one, and we will be doing I plus plus, so that next element will be pointed again, I plus plus, this will be pointed, and so on. So I plus plus here. So print f percentage d q of I. Wherever we are present at that time, q of I will be printed. I will be present here in the first case, 1 will be printed. I plus plus, this will be printed. I plus plus, this will be printed till we reach this point. Okay, this is how you print the q elements. Now second one is second type of queue. The first one which we discuss is the linear queue. Okay, it is called as a linear queue. This is the second one which we are discussing. It is the circular queue. Okay, so why do we need a circular queue? It will be like this. The end will be attached with the beginning. Okay, the end will be attached with the beginning. This is the end and this is the beginning, right? So end will be attached with the beginning here. And why do we need it? Okay, like let's understand why do we need it. In linear queue, there comes a point where the rear will reach the end. Okay, rear is present here and we cannot insert any more elements here, and rear cannot go back also in the queue. That is the functionality which we have defined. Rear will go plus plus only and front will also plus plus only. After a point, we cannot insert any more elements even though the space is present here. So what we'll do, we will wrap this item here. So what will happen, the further elements will come here. So we'll be able to insert after doing our plus plus in the beginning here. That is why we need the circular queue. Okay, so deleting 1 f will become like this, deleting 7 f will become like this, and deleting 8 f will become like this, and front and rear are present here. Even though the queue is empty, we cannot insert any more elements here. So what we do is we use a circular queue so that r plus plus will happen here. After r plus plus happen, insert 12. 12 will be inserted at this position and front will be here. So circular queue does not give us the limit of having the space and not able to insert. That thing will not be there, okay, in the circular queue. So we'll be using the circular queue. So here also the code remains the same. Whatever the code we have discussed for the insertion, deletion, and the display, it will remain same, except that one thing will be different, which is f is equal to 0, r is equal to 0. In the linear queue, f is equal to -1 and r is equal to -1, right? So it will be starting from this position. Here it will be 0 and 0 because there is no -1 position. It will be circular queue, means it will be connected. So it will be starting from here. And since we had been doing r plus plus and f plus plus, we will be not doing the same thing here. Slight difference is there. Okay. So this is the representation of a circular queue with n is equal to 7. 7 spaces are present here. Okay. So now we will be using the rear is equal to rear plus 1 modulus size. Okay. So what is rear? Rear will become rear plus 1 modulus size, and front will become front plus 1 modulus size. So why do we use these formulas, and why not r plus plus and f plus plus? This is a natural question which will come, right? So let's have a look at why that's the case. Suppose that n is equal to 7 and r is equal to 6. R is present here, okay, and total number of spaces are 7. Now our question is to insert 12. Okay, so what we can do, easily we can do r plus plus and insert 12, right? But what will happen if we actually try to do that? So q of r is equal to 12. Okay, first r will be made as r plus plus, which is r plus 1. R is equal to 6 now. 6 plus 1 will become 7. R's value is 7. So as you can see, there is no 7 index present here. If you do r plus plus, we will get an invalid index. That's why we need to use this formula. How this formula works? This formula, if you insert 6 here, what will happen? 6 plus 1 is equal to 7. 7 modulo 7, it will take the remainder. The remainder of 7 divided by 7 is 0. So we'll be reaching this position here. Okay. For rest of the position, we can do r plus plus, but at this specific position, we need to do this one, modulo size. Why? Because we need to get the starting position, and we'll get the starting position by using this formula. Same goes for the front also. Okay, front plus plus will be replaced with f plus 1 modulus size. Okay, this was related to the static allocation. We are fixing what is the size of the circular queue. Like for example, here we fix the size as 6. I mean 7, right? So that is called as static. But we can also change it dynamically during the execution. If the requirements is there, we can change. That is called as dynamic location. So here the function will be altered as follows. Int rear will become rear plus 1 modulus capacity, and we will be checking if front is equal to rear plus 1 modulus capacity, then q full will be printed. Else if it is not full, what we'll do, we'll just increment the rear value and put the item there. Okay, this is how you add it using the dynamic allocation. Now to use the dynamic location actual method, which is the q full, here what happened, we called q full, right? So q full means it will double the capacity. Okay, now let's have a look how the capacity will be doubled. Okay, you need not go into the depth, just understand what's happening here. Q full is present here, and the star new q is coming here, and this new q is initialized with in star malloc 2 times the capacity of the size of int. Okay, 2 times the capacity it will be there. Like for example, if the initial q was 6, it will become 12. If it was 8, it will become 16, and so on. Okay, so double size will be present at new q. And what we'll be doing, we'll be using the start value and the end value, and we'll be copying the old queue into the new queue. Okay, we'll be copying the old queue starting and ending position we have specified into the new queue. Once we have done that, we'll be able to use the new queue, and here we'll be specifying the front, the rear, and the new capacity, and free queue will be present here. So queue will become the new queue. Okay. The next one is the DQ, which is known as doubly-ended queue. Okay, in doubly-ended queue, it will be like the normal queue only. But what happens? A DQ is a queue where the elements could be added or deleted at either ends. Okay, when there is a queue, in queue will be inserting from here and deleting from here only, right? But in the DQ will be inserting and deleting from this end as well as this end. Okay, so that is called as a DQ. Okay, so the operations and codes, everything remains same. Just that a code needs to be added to add elements at the front end and delete at the other end. Okay, so that is the only difference in the coding part. Also, if you go through it once, you'll be understanding the code as well. Priority queue is the one where we will be having the elements processed in a priority order. There will be priority for each element, which this element is to be processed first, this is second and third, and so on. Okay, so based on the priority they'll be executed, not based on first in first out or last in first out like in stacks and queues. Here we'll be having the priority if two elements have the same priority. Okay, if two elements have the same priority, which will be given the consideration, they will be processed in the order of insertion of the elements. Which element got the first insertion, that will be processed first. Okay, another type of queue we have is the multiple queue. In multiple queue we'll be using 2D array. Okay, we'll be using 2D array to represent it. Now see, here we have the priorities present. J1 to J6 is present here, and the priorities are given here. So J1 and J2 have the highest priority 1, the J3 has the priority 2, J4 and J5 has the priority 4, and J6 has the priority 6. How do we represent it? Using 2D array. Okay, in 2D array what we do, we'll put, write here 1 to 6 and here also 1 to 6, because 6 jobs are there and the priorities are also 6. Okay, so this will represent the priority. Okay, this is the priority and this is the jobs. Okay, now see, the first two are J1 and J2, those priority was 1, right? So here in the priority 1 we'll putting J1 and J2 in that order. First J1 came, then J2 came. Next we'll be seeing the priority 2, which is the J3. Okay, so priority will be having J3 here. Then we have the J4 and J5 with the priority 4. So we'll be skipping this row here. There is no job present. In the fourth row we'll be writing J4 and J5. After that in the J6 means sixth row we'll be writing J6. This is how you represent the queue, multiple queue in the 2D array. Okay, and here also the delete and insertion operation happens. If you want to delete the means the element, what we do, we find the smallest k such that front of k is not equal to rear of k. Front and rear are not equal, that element will delete first, and which is the smallest such element. That means first non-empty queue. First non-empty queue is which one? This one. So the based on the priority, this will be deleted first, then this will be deleted, then this and this. Okay, that's how you do the delete operation. Insertion operation will be inserting element in the row of p minus 1 of the queue. If there is another row here present, based on the priority we'll be inserting at that point. If the priority given is 2, at that time we will be putting it here. Okay, here j7 will come here in the 7th. Okay, like that, which queue is required, that row will be putting the value. Okay, so that is how the deletion insertion happens. We have the multiple stacks as well, like how we implemented the multiple queues, right, using 2D array. Like that only multiple stacks will be there. Here a new stack is placed on the top of bottom of the stack. There is one stack here, a new queue will be present, a new stack will be present on the bottom, another new queue on the bottom of this. Like this, it will be keep on increasing. Okay, that is called as the multiple stacks. So this is one stack. Okay, and this is second stack, and this is third stack, and so on. Okay, so here this is bottom 0 and top 0, this is bottom 1 and top 1, this is bottom 2 and top 2, and so on till bottom n it will be, where m is the memory of the size of the stack, the total memory how much it's occupied, that will be m, and n will be number of stacks, 1 2 3 4 and so on, how many stacks are there, this is one stack, and so on. Okay, so based on that number you can calculate the starting address of this one. This will be 1 into m by n, 2 into m by n, and so on till m minus 1. Okay, and function to add an item to the stack I. If you want to add an item to the stack I, what we'll do, first we will take the element here int I, and which element we want to insert, that one will be taking in item, and I is the which stack we want to insert. If top of I is equal to bottom of I plus 1, that means stack is full. What does this mean? Top of I and bottom of I plus 1. Top of I means if the top one has reached this point, okay, where it is equal to bottom of 2, that means this stack is full. When this stack will be full, then only top will go here, right? So that means the stack is full when it is equal. This value and this value, if both are equal, that means the stack is full, we cannot add the element. Else we'll do plus plus top of I, and then we'll be adding the item there. Okay, means the top is present here, the top will be taken here and it will be added here. Okay, in case it is not full. want to delete the element from the stack, the same thing, which element, which stack we want to delete the element. If top of I equal to bottom of I, that means stack is empty. Top of I equal to bottom of I means what? Top of I and bottom of I at the same position, that means this stack does not have any elements. If it had any element, top will be pointing to that element, right? And it will not be equal to bottom. If it's equal to bottom means there is no element present. In case there is no element present, deletion is not possible and we will return the empty stack of I. Else we will return top of I minus minus. This will ensure the deletion of the stack element from the stack. Okay. Moving to the second half, which is the linked list. Here we have few topics. Introduction to the linked list. What is a linked list? Linked list is, as its name specifies, list of items that are linked. Okay, there will be items present which are linked with each other. Now let's understand how they are linked with each other. So this is an illustration. Here will be first. Here will be link of the second element, and here will be having the link of the third element. Here will be having the link of the fourth element, and so on. And last element will not have any link present because that's the end. Okay, and the data will be present here. Along with that, one link will be present which will be pointing to the next element, and this will be present here data. Another link will be there which will be pointing to the next element. So like this the linked list is represented. Now what is the advantages and disadvantages? First let's understand what is the advantages of a static array. Static array is the one which we discuss. Normal array which we discuss, which we declare using a fixed size. So what is the advantage of that? And data accessing is faster, because if there is a static array, we know the index where we want to access, we can directly access it. Like for example, if the array name is q, if you want to access the fourth element, q of 4 is equal to print q of 4. What will it will print? It will print the fourth value. So data accessing is faster. That's not there in this case because there is no index present here. You have to traverse all till this point and then we need to print. Okay, this we will be discussing in the upcoming topics. For now, just understand that the static array is faster and it is simple to understand. Just declare it and insert the elements in sequential order and access it also. Disadvantages of array is fixed size. If you want to insert more element, that's not possible. Array size cannot be increased by adding element at the middle. If there is an array already filled here, we cannot add anywhere in the middle, there is no space. But in the linked list, what we can do, we can add another linked list here and we can point this and this like this, so a new element will be inserted in the middle. Okay, that is the advantage. So what is the advantages of the linked list? Size is not fixed. Data can be stored in non-contiguous blocks. It can be in different parts of the memory. Just a link is necessary. Insertion and deletion is efficient here. The disadvantages are there. More memory is required. Why more memory is required? Because we need to also store the link of the next address. Along with the data, we are storing the link also, right? So that will cost extra memory. Difficult to access arbitrary element. Arbitrary element means if there is a linked list present here, if you want to access this element, okay, we cannot directly access. We have to start from here, go to this, go to this, go to this, and then only we can access this one. Okay. So that is the disadvantage of the linked list. Very important question from exam point of view. Next, there are four types of linked list. Okay, in this module we'll be just discussing the first two. Next module we'll be discussing the next two. Okay, so here let's understand what is singly linked list. The one which I showed you at the top, that is a normal linked list only. So here understand very carefully. See, first has a number here. Okay, 343. What is this? This is the address. Okay, this is the address. Address of what? Address of the next element. Okay, whatever address is present here, that element will be having that address here. Okay, based on this address only we are filling this value. Okay, so we will be filling this value, this will be pointing to this. By using this address we can reach this element, take the data, and this will be having the address of the next element 344, and this will be pointing to the next element, and so on. This is how the linked list is. These two parts, data and the link part, and this whole thing is called as a node, and this has an address as well. Okay, so let's have a look at the C code for implementing the linked list. Here we'll be having a struct. We'll be using a struct here, okay? Because we need two things here. One we need is the, so struct name is node here, and opening and closing parentheses are present here. We need two things. First is the data part we need, and second is the link part. So in the data part we have the int info. So info will be having a information what is the data we need to have in the node, and we'll be having a link part also. Link is what? Link is a pointer, and pointer of which type? Pointer of the type address. Address of which? Address of the node. So here we are using address which is of the type node. So the type node is present here. That same type pointer we need, because the address is stored in the of the data type node, right? So we need the link of the pointer which is pointing to a node only, right? So that's why we do struct node star link. This is also called as a self pointer or self-referential structure. Okay, and for simplicity purpose we'll be type def also. We'll be type defining, means instead of this name we just want to use node. How we can do that? Just write type def here, struct node, and write node here. So instead of writing struct node, we'll next time use node only, which denotes we are using struct node here. Okay, this is what this line of code does. This is called as type def. Okay, So after a node is created, we have to create a new empty list as follows. Okay, after a node is created, we have to create a list as well. So the first list will be null. Okay, the first list will be pointing to null. Okay, what is first? First is this. Here it will be pointing to null. There will be nothing present. It will be pointing to null. There will be no more elements present here. Okay. After that only slowly we'll be adding the elements as they come. Okay. So let's understand that how to add the elements. Before adding the elements, you need to understand that the pointer first stores the address of the first node in the list. Okay, so if there is a list present here, the first node's address. Okay, this first node's address is stored where? It is stored in first. First is a variable of the type node. Here it will be stored the first address. Okay, first will have the address of the first node. Okay, to obtain the node, what we do? First is equal to node star malloc size of node. We'll be allocating a dynamical memory present here, and then in the info part we'll be writing 5 here, and in the link part we'll be writing null here because this is the only one node. Okay, so this is first, and first info will be 5, and first link will be null here. Okay, this is the first node which is created. Now let's understand the singly linked list. In single linked list, it's a normal linked list where each node is connected to the next node. Okay, so this is the type of the node where we have the nodes connected with each other with the info and the link part. This is the same thing which I showed you initially the first diagram. So here we'll be having the info part, and this will be connected with the next node, and this will be connected with the next node, and so on. Okay, so here we'll be seeing the C implementation of the insertion. Okay, so there are two concepts here, the front and the end. Okay, we can insert or delete at the end, I mean the front, and we can insert or delete at the end as well. Okay, on both sides we need to understand the coding perspective. Okay, after you understand the code for the linear linked list, for the other all the codes you can derive it by yourself. Okay, because the understanding of concept is important here, so pay attention. So here we have the function void insert front. What we are trying to do here, we are trying to insert another element here. Okay, so what we are doing, we are getting that element here, int item. Okay, and then we are creating our node start temp. Okay, okay, so let's illustrate this how it happens. Node start temp is created. Okay, so this is for example temp. Okay, now temp is created, it is empty here. Next, what's happening? Temp is equal to node star malloc size of node. So some memory is allocated here and it's present somewhere. Okay, now if temp is equal to null. Okay, for simplicity purpose, let me add temp here because their address also will be written. Okay, let's understand this like address. For example, this is 1x3. Okay, the address of the temp is 1x3. Okay, now if temp is equal to null, that means no space is available. If temp is not allocated, that means there is no space available and we cannot add any elements. Okay, if the temp is not null, that means it has some like it is allocated, we have space present here. Okay, that's what means temp is not equal to null. That means it has some space here. Okay, else what we need to do, temp or arrow info is equal to item. Okay, what we do, temp arrow info is equal to item. Now we have taken the item here. Okay, let's suppose that item is an integer value. Item has the value 5. Okay, now what we do, this is of the type int. Okay, and temp is of the type node. Okay, so node will have two things. First is the data part, second is the link part. This is the data part, this is the link part. Okay, temp arrow info is equal to item. So in the info part, items value will be stored here. So 5 will be stored here after this code. And next, temp arrow link is equal to first. Temp arrow link, this is the link part, that will be pointed to first. Okay, that will be pointed to first means suppose that initially first was this first, and this had an address 345, and it was pointing to another linked list 345 here with some data in the link, and this was pointing to some other, and so on. Okay, now what we did is temp is equal to temp arrow link is equal to, okay, temp arrow link is equal to first. That means temp arrow link is this point. This point should have what? First. This point should have first means it will be having 345. Okay, the first value is 345 and that will be stored here. So indirectly what happened, 345 is getting pointed to this one. So what we did here is, this was the initial list and we added another node here. Now how the node is, this is temp. Okay, and this is 5, and this is 345, this is temp, and this is pointing to the first element which was initially present 345, and this was as usual initially. Okay, so now another element is added here which is at the front. Okay, this is called as inserting at the front. And next what we do, first is equal to temp. First is equal to temp means now first should have the address of the temp because temp is the first element and first always has the first element. Okay, so here we'll be writing 1x3. Okay, so here first when we do first is equal to temp, the value of temp will be stored in first. Now first is pointing to temp and temp is pointing to this one. So initially it was like this. Now we have added one element at the front. Okay, this is how the insertion at the front works. Okay, Now like that only insertion of the node at the end of the linked list. Okay, so suppose that we have a linked list present here, and this is first is pointing to a element here. Okay, I'll not write any address or the data, you just understand what's happening here. Okay, so this is the end. Now what we need to do, we need to create a new node. That's the first step. Create new node. Okay, create new node, and after creating the new node we have to attach this node to here. Okay, so how do we do that? So after creating the new node, what we need to do, this link part, right, the link part of the last node, okay, that is to be attached with the address here. So after creating the node, we need to get the address here. After getting the address, we need to access this node. From the start we will traverse like this, like this, like this. We will come here, access this node, and in this part we will store this value. Okay, that's what the code is also doing. So we'll store here, insert rear. Okay, void insert rear int item will be taken, and in star temp and star cur. So temp is the pointer and cur is also a pointer. Two pointers we have created. Let's make this pointers here. So this is temp. Okay, and this is current pointer. Okay, and this is the initial linked list. Okay, let's make it simple. Okay, so this is the initial linked list which we have here. It will be having three nodes. Okay, now understand 11, 12, 13. These are the addresses present, and in the first we have 11 here, and this is having 12, and this is having 13, and here we'll be having nothing present. Okay, so this is the things present here. Now temp and cur is also created. Let's temp has a 16 value, and this has the address 17. Okay, now what we do, temp is equal to node star malloc. This is allocation of the node. Temp is done here. If temp is equal to null, if temp is null, you will be returning it, but that's not the case here. Temp of info is equal to item. We are taking an item here, right? So let's suppose that item is equal to 6. Okay, or 6 or 8. Item is equal to 8. Now temp of info is equal to 8. So here we'll be writing 8. Temp of link is equal to null. This will be having null. Okay, so this is initialized here. Next, what we are doing, if first is equal to null, is first null? No, it's not. If first is null, that means temp will be the first element. So first will be pointing to temp and will be returning temp. See, if first is null means there is nothing present here, and we need to have one element which is adding at the end. So if there is nothing present, this is only the end. Here we will be pointing to the temp, and that will be returning. So first will become temp and will be returning that in case there is no element present. But here, since there are element present, what we'll do, cur is equal to first. Okay, what we are trying to do, cur is equal to first. So cur will have one value which is first. So it will be having 11 here. Cur is pointing to the first value which is having 11 here. Now also what we'll do, while cur arrow link is not equal to null. Okay, cur arrow link, what will be in cur arrow link, the same thing which is present here, that will be 11. Okay, so it will be pointing to 11 here. Okay, the data part will be empty. Cur arrow link will be having 11 here because cur is equal to first, right? Cur is equal to first, so whatever first has, that will be copied to cur. What first has like this, right? It is having 11 address and no data. Cur will also become the same, which is 11. That's the same thing which I wrote here. Okay, so this will become cur, and then while the condition was this, right, while cur arrow link is not equal to null, till this point we have to iterate. Okay, now what we are iterating inside this, cur is equal to cur arrow link, that's all. That's the one step we are doing. Cur is equal to cur arrow link. Okay, what does this statement ensure? This statement ensures that cur's value will be changing always. Cur's value will become cur arrow link. Okay, what will cur's value become? Cur arrow link. That means cur will become this one. Okay, cur arrow link means 11, so cur will become this one. Now when cur becomes this one, the value which is present here, that will be inserted here, which will be 12, right? Then again cur's value will change. Cur is equal to cur arrow link. Cur arrow link is 12, so cur will become what is in 12, that is this one. So this will become cur. So it will become then 13 here. Then again cur is equal to cur arrow link. Cur arrow link will be pointing to the 13, and this will become cur. Okay, and this x means null. Okay, so cur will come here, and this will become null here. Okay, now the cur's value present here is null. Okay, so this condition is will be falsified, which is cur is not equal to null. So we have reached this point where cur is pointing here. After that, what we need to do, after that what we'll do is cur arrow link is equal to temp. Okay, cur arrow link is equal to temp. What does that mean? Cur arrow link means this point should become temp. This point should become temp means the address of temp should be stored. That means 16 should be stored. Now what will happen when I store 16 here? When I store 16 here, that means cur will be pointing to the temp here. Okay, so what just happened, a new node got added at the end. That's right, a new node got added at the end of the linked list. This is what the function was about, right? So this is how you insert at the end of the linked list. And this code here this is the traversing code. Means if you want to traverse the code, you'll be using this code. Okay, we'll be taking cur as this one first, and there will be cur arrow link, cur is equal to cur arrow link, cur is equal to cur arrow link, and we'll be traversing till the end. This is called as the displaying of the nodes. At each point when we traverse here, we can display like this: printf cur arrow info. When we do that, at each point we'll be displaying the information as well, right? So that's how you do the display operation also. Okay, so next is the one where we have the insertion of an element after a node with the location lock. Okay, so what does this mean? Let's make some nodes here. Okay, okay, these are connected with each other. Okay, they have the indexes and the values also present, and first is present here, that is pointing to the first node. Now what we need to do is we need to create a new node. Okay, this is the new node, and this new node needs to be inserted after lock. Okay, suppose that lock is this one, which is they are referring to location. Okay, after this node it needs to be added new. So how will be the after effect of this one? After effect will be like this. Okay, this will be here, lock will be here, second one, and here new will be there, new, and here three nodes will be made. Okay, so this thing we need to do, we need to create a new node first, and then after the location we need to access the location by traversing, like how we did in the previous question. We need to come here and we need to point this link part to this address, and then this link part to this address, so that this will be inserted in between. Okay, so that's what this code will be doing. So let's quickly go through it. Here we'll be having the temp and the next year, and temp will be node star malloc size of node. Temp will be allocated. If temp is null, there is no space available. Else what we'll do, we'll take temp of info is equal to item, which we are creating the temp. Okay, temp will be creating and we'll be having the info item attached here, and yeah, attached here. And after that, next will be equal to location arrow link. Since we already have the location, we can directly access location arrow link. Okay, location arrow link will ensure this point. Okay, this what will be stored here, this value will be stored in the next. Okay, means the link value will be stored in the next. Okay, next will be stored inside the next, what we have, location arrow link. Okay, now what we do, location arrow link is equal to temp. This location arrow link here, what should be stored here, temp value should be stored, whatever the temp value we have created. So that will be pointed to temp. After the location, temp will be pointed, and then temp's link value should be next. What did next have? Next have the location's next value, right? So let me again explain it properly what's happening here. See, okay, understand this very carefully. Temp arrow info is equal to item. Okay, temp is created here, and in temps info we will be having some information here. Okay, like suppose 10 was present. Okay, item was 10 and temp arrow info is item, and this is 10 here. Now this is location. Okay, so let me zoom it a bit here. This is location, and the next value is pointing to the next value here. Okay, let's suppose initially it was this case, right? Let's suppose it was xyz. Okay, now the address is present xyz here, which is pointing to the next node here. Now temp is coming, temp has to come in between this one, right? So what we do, in next we will store location arrow link. Okay, next will be a variable created, and in next we'll be having location arrow link. What does location arrow link have? Xyz. So in next xyz will be stored. Next what you need to do, location arrow link is equal to temp. Location arrow link, this part should be replaced with temp. Okay, temp's address, that will be replaced with. Okay, what is temp's address? Let's suppose that abc. Okay, so temp's address will be stored here, abc. So what happened, this link was pointed to this one. Next what we need to do, this link needs to be pointed here, and this address will be have in the next. So this will be equal to next. What is this? This is nothing but temp arrow link. Temp arrow link will be ensuring this one. Here what you need to store, next. Next is has the xyz. Xyz will be pointed here, and then this will be pointed here. That's what it is. Temp arrow link is equal to next. Okay, so this is how you insert element in the middle. Okay, if this is the row, we have to insert an element in the middle. This is how you do it. Okay, next we have function to delete a node at the front of the linked list. So we'll be doing the same things. We'll be taking a current pointer. If first is null, means the list is empty. Else we'll take the current is equal to first. We'll do first is equal to first arrow link. What happens when you do first is equal to first arrow link? Okay, so this is first. Let's suppose that it has abc address, and abc is having a pointer here, and this has some data 12, and this is pointing to def, and def is another node here, def, and this has the data 13, and this is having null value. Okay, so what will happen when we do first is equal to first arrow link? Inside first, what should be stored? First link part. First link part is what? Def, right? first link part is DEF. First is pointing to ABC and ABC is pointing to DEF, the link part, right? So in the first, what should be stored? DEF will be stored. So when DEF will be stored, what will happen? The first will be pointing not to here, it will be starting pointing here. Okay, so what happened to this one? This will be not pointed, and the starting will be considered from here. Okay, the starting will be considered from here, and this will not be considered. And then this was stored in cur. Okay, this was stored in cur because we had done cur is equal to first initially. So cur had this value. What will do? Free cur. Free cur means this will be de-allocated memory. So this memory will be deleted from the memory after using free operation, and then it will be used for some other purposes, right? So this is how you delete at the front. Deleting at the end is also same, just that you have to traverse till the end, till first arrow link is not equal to null. First arrow link is not equal to null means till when you get the null value here, that time till that time traverse there, and after that point you have to initialize this one at the means you have to free this one, but before that you have to make this part as null. Okay, this part as null you have to make. For that you will consider two pointers, previous pointer. Okay, previous pointer will be there one place behind this one. This is previous and this is current. Okay, let me explain how this happens. Okay, so see, deleting at the end. Okay, let's consider one example. First is here and this is pointing ABC, and ABC is present here, and this is pointing to DEF, and DEF is present here, and this is pointing to XY, and XY is present here, and that is pointing to null. Okay, let's suppose this is the case. Okay, now what you are doing, previous and current, two pointers we are creating, prev and current. Okay, two pointers we are creating. Okay, this will be having some values. Now what we are doing, if first is equal to first of link is equal to null, means first link part is null, that means this is the only element. In that case what we will do, current is equal to first, first is equal to null, free current. Current is equal to first means current will be having this value ABC. After that we will be doing first is equal to null, first will be replaced with null. Okay, after that free current means this will be freed. So if first is null, it will be not pointing to anything, and current will also be free, that means this node will be deleted. Okay, that is the case when we need to delete the element where the front is null. Okay, the next one is where the front is not null. In that case what we have to do, we have to traverse till the end. Okay, we have to traverse till this point, and then we have to delete this node. Okay, so after deleting this node we need to clear this address also, right? XY address, this also address we need to clear. So how we will do that? Okay, so how we will do that? We'll do that by having a previous counter also. Okay, means previous will be pointed to this one and cur will be pointed to this one, and we'll be incrementing it one by one. Okay, when we find out that the value pointed to by current is not equal to null. Okay, so let's suppose the previous is equal to null initially. Okay, okay, so here what's happening, the previous is equal to null. Okay, initially we are making it as null, previous is equal to null, so previous is not pointing to anything and current is also empty. Next what we are doing, while current arrow link is not equal to null. Okay, while current arrow link is equal to null, let me take this down. Okay, now see, previous is equal to null. Okay, so this is null here, current is equal to first. Okay, so current will be having the first value, this is not null, this will be having ABC. Okay, okay, so current will be having ABC here. Next what will happen, while current arrow link is not equal to null, what is current arrow link? ABC's link part. ABC's link part is DEF. Is it null? No, it is not. What we should do, previous is equal to current. Previous is equal to current means previous will also be having ABC value. So both previous and current are pointing here. This is previous, this is current. Both previous and current are pointing here. Current is equal to current arrow link. Current is equal to current arrow link means current will be having current arrow link means DEF. So current should become DEF. If current becomes DEF, then current will be pointing to DEF. Okay, so current will be coming here. Okay, this is current now. Next what is happening, we will be doing until we get current arrow link is equal to null. Okay, we'll be doing this, then again repeat, previous is equal to current, we'll take previous is equal to current. Okay, this is previous and it will be equal to current. Again we'll be checking if this is null, means current is equal to current arrow link, we'll be taking current arrow link, we'll be taking current here, and we'll be checking if it is null. If it is null, what we need to do, we need to not increment this one, we need to stop the execution. After that, what will happen, we'll do free current. Okay, free current will previous link part, this will become null. So what happened here, the last node got deleted, right? And this also became null here. This is what deleting at the end. Okay, the next one is the traversal of a linked list. Okay, so a traversal means we are traversing, means we are accessing each element and traveling one by one. Okay, so if there is an whatever we did till now, that is traversing only. Okay, so if you have n number of elements, we are traversing it one by one, checking this one, then checking this one, checking this one. That is called as traversing, and it is used for searching an element. Why it is used for searching an element? If you want to see if any of the nodes item value is equal to 5, what we'll do, we'll check this one, we'll traverse here, check this one, check traverse here, check this one, for searching an element if it's present in the linked list or not. Inserting a specific location, we discussed the location part. After this location we want to insert, we are doing the traversing again, and after this location we are inserting the value. And next is display the elements. For this linked list we are traversing each value, printing the info value, going here, printing info, and so on. Okay, that is the code. So the official code will be this one. We'll be getting a first here, so first we'll be getting, and current also will be getting. If first is null means list is empty, else what we'll do, current is equal to first. Okay, we'll take current as first. So this is f, and this is pointing here, 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 and it has the links in between. Okay, so current will become first. Whatever the value is here, that will be coming in current. So current will also be pointing to here. Okay, after that, printf cursor, current comma info. What is the info part of this one? That will be printed, and then current is equal to current arrow link, means current arrow link is pointing to this one, so current will become this one. Current is equal to current arrow link. Now current is this one. It will print the value, then it will go here. It will print the value, it will go here. Till when it should happen? It should happen until current is not null. When this will go at after this point, the current will be pointing here. This is null value, right? So it will be stopping the execution. This is how you display the nodes. I mean the nodes you will be displaying. Okay. The next one is the function to concatenate two linked lists pointed by list 1 and list 2. Okay, you have to concatenate two linked lists. There is one linked list here L1, and this is another linked list here L2. You have to concatenate, it means you have to connect this one with this one. So, and linked list will be having many separate nodes which are interconnected. So to concatenate this one, first we'll check if list 1 is null. Concatenation of null and list 2, that will be equal to list 2 only, right? So we'll return list 2. If list 2 is null, we'll return list 1. Else what we will do, we will take temp is equal to list 1. Okay, so temp will be equal to list 1. Temp will have all the list 1 nodes here, and what we need to do here, we need to traverse till the end of this. After that, take this link part here and attach it with the first node of list 2. List 2's first node, if it is attached with the last node of list 1, that means there is a concatenation happened. So that's the same thing we'll do. We'll traverse till temp arrow link is not equal to null. Temp arrow link will become null at the last one, and till that point we'll do temp is equal to temp arrow link. Like this, will traverse temp, 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 and it will come here. After this point, what we'll do, we will temp arrow link should be equal to list 2, right? List 2 is the one which is having the first node's value, and that will be assigned to the temp arrow link, means the last node's link part will be the first node pointed to. Okay, so when you do that, there will be a concatenation happen, and we will return list 1. Why? Because the node is starting from the list 1. This is the list 1 that is concatenated with the list 2, so the starting part is the list 1, will be returning list 1. Okay, then function to reverse a linked list is a very very important question from the exam point of view. The reversing of the linked list. So here we have the node star reverse, struct node star first. Okay, let's create one representation here. So we'll be having f here, we'll be having 1, and this is pointing to the address 1 here, and this is pointing to the 2, 3, 4. Let's suppose that there are 4 nodes here, and this is pointing to 3, and this is pointing to 4, and this is pointing to null. Okay, so this is present initially. Okay, now what we are doing, let's go through the code. Current is equal to first, so current is pointing current is equal to first means what is value in the first, there current will be pointing, so current will come here. And previous is equal to null, so previous is equal to null means previous will be present in the null part. Okay, previous is present at this point, which is null, while current is not equal to null. Is current null? No, it's not. Next is equal to current arrow link, so next we will be having next will be having current arrow link. So where will next be pointing? Next will be pointing to current link part. Current's link part is 2, so next will be pointing to 2. Okay, next will be present here. Now current arrow link is equal to previous. The current's link part should become previous. If it becomes previous, it will become null, because previous was what? It was null. so this became null here. Okay, so it is pointing to null. That means this is pointing to null here. Okay, then previous is equal to current. What will do? Previous is equal to current means the previous should become where the current is pointing to. Previous comes here, and then current is equal to next, and current will go to the next. Okay, now current will come here. Again the same thing will happen. Current is not equal to null. No, it's not null. Then next is equal to current arrow link. Current link part, that will become next. Okay, what is current link part? 3. So next will become 3. Okay, so next will come here. This will become 3. Next, what we are doing? Current arrow link is equal to previous. Current link part is equal to previous. Previous is this. So current link part will be pointing to 1, right? 1, which is previous. So it is pointing like this. Okay. Next, what will happen? Previous is equal to current. So after this point, previous will become current. Previous will come here. Then current will become next. Current will go here. Okay. Current has gone here. Now what's happening? Again the same thing. Current is null. No, it's not null. What we need to do? Next is equal to current arrow link. Current arrow link is 4. So next will become this one. Next will become 4. Okay. This is next. And after that, what we are doing? Uh, current arrow link. Current arrow link is equal to previous. Current link part should become previous. What is previous? Previous is 2. So link part should become 2. So here we'll be putting 2. Okay. Here we'll be putting 2, and that means it is pointing to 2. This node is pointing to this node, like that. Okay, this node is pointing to this node. After that, previous is equal to current. Previous will come here, and current will be here only. Next is what is the current is equal to next, so current will become next. Okay, so here current will come. Now what's happening? After that, the same thing. Current is null or not? Current is not null, but current arrow link is null. But we not consider that current is null or not. No, it's not null. Next is equal to current arrow link. So next will go. Next will be pointing to null. Okay. So here next is there pointing to null. Okay. And current arrow link is equal to previous. Current's link part null. Null should become previous. Previous is 3. So null should be removed here and it should become 3. Okay. So this arrow will be also changed. It will become reverse here. Next, after that, previous is equal to current. Previous will be removed from here. It will become current, and then current is equal to next. Current will become next. What is next? Next is null. So current will also become null. Okay, current and next both are pointing to the same point. Next will come here. Current is null or not? Yes, it's null. So this will not be executed. After that, return previous. Return previous means the previous is pointing to this point. This will be returned. This will be returned means whatever is returned that will become first. Okay. So this is returned means this became first. First is pointing to P, which is 4. Okay, so see, as you can see, the linked list is reversed. Okay, this is how the code you'll be doing for the function to reverse a linked list. Very, very important question from exam point of view. Okay, next we have two topics, which is implementation of stack using linked list, implementation of the queue using linked list. Stack and queue, it works on LIFO and FIFO. LIFO means last in first out. So here only insert and delete at the front needs to be implemented. Okay, so when there is a linked list present here, if you want to implement it using a stack, the item should be coming from here and deleted from here. That is front, right? That code you have to implement. Okay, if you go through it once, you get to know. You can go through the official notes. And the second one is FIFO, which is the first in first out. Only insert at the end and delete at the front. Okay, insert at the end and delete at the front. Okay, insert at the end and delete at the front. So here what's happening? This is the linked list. Suppose that this is the same linked list present here, and insert at the end. Insertion is happening from here and deletion is happening from here, because whatever is coming first, that needs to be deleted first. Okay, so these codes you have to implement, the insert at the end and delete at the front. Okay, easily you can understand. You can go through the notes. Moving on, we have the linked stack and queues. Okay, this is linked stack and queues. So this is how the linked stack will be present. The top will be here and each will be pointing to the next one, and the link queue will be like this. The front will be here and the rear will be here, and this is the data and the link part. Okay, this is the link queue and this is the link stack. Okay, moving on to the last topic, which is a circular linked list. In circular linked list, we will be having the same linked list here, except that the last node will not be null. It will not be null. Okay, it will not be null. Okay, instead it will be pointing to the first element. This is pointing to the first element. Okay, that is called as a circular linked list. So the function to insert an element at the front, this is the front. If you want to insert the element, how do we do? Okay, you want to insert the element here, first understand the logic. Okay, need not explain the whole code, just understand what we need to do. Okay, to insert at the front means we need to create a new node here. We'll create a new node here. Inserting at the front means this part should be pointed to the new node. Okay, this part should be pointed to the new node. After that, this next part should be pointed to the first one. Okay, that's all the code is doing, the same thing. Here what we'll do, insert an item at the front of the circular linked list whose last node is last. Okay, last node is last. This will be last here. We'll be getting that last node, and also we'll be getting a new node. Okay, so to simplify what's actually happening here. Okay, so let's first understand what's happening. This is the last node we have got. Okay, last node. What we need to actually do in the code is traverse till the last. You know the code for traveling, right? First we'll do cur is equal to first, and we'll be implementing while cur arrow link is not equal to first. Okay, here we have to do like this. Cur arrow link is not equal to first. Why? Because cur arrow link, when it's pointing to first, that means it's the last node. Okay, we have to actually they have given the last node here. We need not do this. Sorry, we need not do this one. We can directly go for the last one. Last from here only. Now what we need to do? Last arrow link. Last link part should be equal to new, right? And new arrow link. New link should be equal to first. But first we will not be having like this, right? First is not given in the question here. So how do we do that? But first value is stored in this part. Initially the last will have the first value because it's pointing to the first value in the beginning, right? So first we need to save this somewhere. So what we will do, we'll create first node star first. Node star first is equal to last arrow link. Then we'll be having the first value, and we'll change the last link to new, news link to first. Okay, this is the only code we need to implement. If it's at the end, if you want to insert at this point here at the, so this is the beginning part. If you want to delete, okay, if you want to delete this node here, how you will do that? If you want to delete it, what you will do, just assume what will happen if you delete this one. If you delete this one, this should be pointed to this point, and this address where it is stored here. Okay, and this is first. So what you need to do, first you need to get first. Okay, so first, this is for the deleting of the first node. Okay, let me write here, deleting first node. If you want to delete the first node, this is how you will do it. Okay, first you will take first is equal to last of link. So we got first. Now after that, this is to be deleted, so you will be taking cur is equal to first and keeping it. Okay, so cur will also be having first. Next, this part, last arrow link. What should last arrow link have? Last arrow link should have this value. Where is this value stored? This value is stored in first link part, right? So last arrow link, this value should be replaced with the value present here. First arrow link is pointing to this one. So when I do last arrow link is equal to first arrow link. Okay, observe this carefully. When we do last arrow link is equal to first arrow link value which is present here, this will be stored here. So a link will be made in between these two, and this will be, we'll be doing free cur. Okay, that's all. Deleting and traversing, already know, start from here until you reach this point, traverse, right? The condition will be while for the current, if you take it as current, while current arrow link is not equal to first. When will be current link first? Current link will be first when we are in the last node. When we are in the last node, the current link will be pointing to the first element. So that's how till this point you will be doing current is equal to current arrow link. We'll be traversing to the next node and doing whatever you want to print it, or you want to search for an element or whatever. Okay, so let's quickly go through the insertion at the element at the front. So here this is the code. Take the last here. If last is null, that means nothing can be done. If last is null, means you are inserting it the last only, so last will only become new, and last link will be last will be pointing to the same one. Okay, like it will be a self pointer. Okay, because this is the only node. Else if that's not the case, what you need to do, news link part will become last link part, and last link part will become new. Okay, news link part will become last link part. Okay, so news link part should become what, this, right? And where is this stored? This is stored in the last link part. So news link is equal to last link, and then last link should become new. So last link will be pointing to new here, and news link will be pointing to first here. That's how you insert at the front. Okay, and to insert the element at the end is also same thing. You just have to go till the last, and then last arrow link is equal to new is equal to a new arrow link is equal to first. Okay, that's what the first is, this one, last arrow link. This is how I explained. In the end also you need to do the same thing, just that you need to ensure that you come till this point. Okay, after if you have to insert this one, actually the inserting at the end and inserting at the first, both are the same thing, because it's a circular queue, right? So just that you will be denoting it as the last whenever you insert the last, and the first will be this one when you insert at the front. Okay, same node is getting inserted in the insert at the front. This will become the first. Insert at the last. This will become the last. Okay, that's all. If you go through the code once, you'll be able to understand. Just trace the code. Okay. So this is the code for inserting at the end. And next we have function to find the length of the circular linked list. Just traverse the linked list. Each time do the count plus plus whenever you traverse at the node until you reach the last node. Okay, then print the count. We have two types of linked list. Header linked list. Okay, inside header means there will be a header node. Okay, the first is a grounded header list. We will be having a start as the header node here. Header node will be just having the link part here, which will point to the starting of the link data. And circular header linked list means here will be having a header node as well as if the last node will be pointing here back. Okay, circular linked list we will be discussing in the next module. Okay. So polynomial representation, we can represent the polynomials using the linked list. So for polynomial representation, so give me an example, 6x square. Here we have two things. This is the coefficient, this is the exponent. So we need int coefficient, int exponent, and also the link part to point to the next element, because obviously we will be having 6x square plus 3x plus 4. This is a node. This will be a node which will point to the next one. This will be a node pointing to the next one, and so on. Okay. So this is why you need a link to point to the next node where it is stored, and type of struct polynode poly. So we'll be using poly to denote struct polynode. Okay, and polynode can be of three types. It can be drawn like this: coefficient, exponent, and link. Okay, so consider polynomial 3x power 14 plus 2x power 8 plus x plus 2, and b is equal to 8x power 12 minus 3x power 10 and plus 10x power 5 plus 3. Okay, so here it is minus 3. Here it will be represented like this: 3 and 14. 3x power 14, the coefficient and the exponent. Coefficient, exponent linked to the next one. 2, 8. 2x power 8, and this is what? 1x power 1, so 1, 1. And 2 is what? 2x power 0, right? 2x power 0, that is 2 into 1. So 2, 0, x. 0 is the coefficient here. Like that only b is also represented. If you want to add the polynomials, let me explain you what actually we need to do. We need to add the polynomials, we need to check if this exponent is equal to this exponent somewhere. X power 14, if it is present here, we can add the coefficient. That is the rule, right? So that's what we need to do in the code also. We will check this one. If this one and this one both are same or not. If both are same, just add these two. If both are not same, if it is 12 means you have to add it here plus x power 12, 8x power 12. If there is 16 here, okay, suppose that if it is 16 here, we need to add 3x power 14 here. Okay, smaller code will be adding afterwards. Okay, 3x power 14. So based on that, now there will be three checks. We'll be checking the exponent here. If one exponent is smaller, another exponent is bigger, that means it will be minus 1. Okay, if you do x14 and x16 comparison, it will be minus 1. If you do x x16 and x14 comparison, it will be 1. It will be returning 1. If it is x14 and suppose that this is also x14, then it will be returning 0. Based on these three values, we will be either putting the value here, either we will be doing this one, or we'll be adding. Let's quickly go through the code. Here we'll be having the polynomial star, and we'll be having poly star a, poly star b. Okay, two polynomials we'll be taking, and here will be poly star c, another polynomial to store the sum. We'll be having temp a and temp b, and last c int sum we'll be having. Okay. Now see, C is equal to polynomial malloc, so we'll be getting a polynomial here. We will be allocating a polynomial for storing the sum. The size will be same as the poly. Okay, and C's link will be null. Temp A is equal to A, last C and temp B is equal to C. While temp A and temp B both are not null, means the polynomials are not null, we will be doing this thing. Compare temp A's exponent and temp B's exponent. If it is minus 1 means temp A's exponent is smaller and temp B's exponent is bigger. That means minus 1. In that case, we have to insert temp B at the end, right? If we have, that means you have to insert temp B at the end. So we'll be passing temp D's coefficient, temp B's exponent, and last C. And we'll be doing temp B comma link here and break. If it is 0 means both are same, that means temp A's coefficient is added with temp B's coefficient and sum is attached here. Okay, and temp A's link and temp B's link will be stored in temp A and temp B. Else we'll be doing the ulta, which is the temp A's coefficient and temp A's exponent will be passing in the last C, and we'll be storing the temp A. Okay, this is the case where the first coefficient is bigger than the first exponent is bigger than the second exponent. Okay, so suppose if a is equal to 3x cube and b is equal to 2x square, this is compared 3 and 2. This answer will return compare operation. If you perform, the answer will be 1. Okay, and copy the rest of the elements, whatever the elements are remaining after that, because not every element exponent will be same. There will be some component like 7 here and 4 here and 3 here which are not going to be added. So whatever is remaining after the all the comparisons, that will be added at the end. Okay. Till temp A will be null and till temp B will be null. In both cases, whatever the elements are present in this temp and this temp, both are added at the end. Okay. And we'll be returning C. Also, we had used attach here. Remember that attach function is also given here. You can go through it. Very simple. We are just allocating our temp here, and temp's coefficient we are taking an exponent as C and E, and rear's link we are taking temp, and rear will become temp, return rear. Okay. Take the coefficient exponent, rear link, rear temp, and return rear. Okay. That is the attaching note at the end of the list. So W increase will be discussed in the module 3, and if you found this video helpful, please do like, share, and subscribe. And thank you so much for watching. I'll see you in the next one.